Cool. Just recap, I guess. We've been talking about source separation, but basically, a mixture of audio and you want to separate them into multiple tracks. It could be, vocal, piano, bass, guitar, drums, but it could also be something else. It could be just each single drums or whatever, vocal, different parts, or even in cinematic case. You can do like soundtrack, dialogue, and effect separation. So one thing to notice that source separation does not remove effects. That's a common myth, kind of. You always get those wet signals out from these source separation model rather than the dry signals. Dry signal is like when you record a guitar or like the vocal close to the microphone, and then you will apply some reverb, things like that. But that's not the topic of source separation. So you always get the wet signals rather than the dry signals that's coming before the effects. Um, and those are called effect removal. We will talk a little bit about it at the end, later part of this course. But it's a very complicated task because it's kind of ill-defined. Because what do you mean by no effects? Think about electric guitar. It comes with effects almost like naturally. But anyway, the mathematical formation is just an equation of summation, which is kind of boring. But the core of source separation is that we do know some prior knowledge of these sources. So there's some way you can actually separate a signal into several different, instruments. So that's what we look into. It's a ill-posed problem. There are so many actually infinite possibilities of these. Um, thing. So the first thing we talk about, is this time frequency masking thing. But basically it's just doing, classification on like each time frequency bin. So basically, you grab an audio, turn it into a spectrogram, and for each single TF bin, time frequency bin, you want to see whether it's for source one or source two or whichever source that is. But basically, you are doing classification. And once you have the mask, you applied it to the original spectrogram to get the output. So this is like a very common approach when we are doing separation. And once you get the spectrogram, you just do inverse STFT to get the original waveform out. So this is something we will look into in the assignment, where we would look into this thing called harmonic percussive source separation, where we basically just use our intuition into percussive sounds tend to be vertical, and harmonic sounds tend to be horizontal in a spectrogram. So we can actually just apply some medium filter to do it. And this is called like harmonic percussive separation. But basically, once you get the spectrogram, you just apply a horizontal medium filter and it will sort of like remove all the vertical lines. And you apply a vertical medium filter, it will enhance the vertical lines and blurry the horizontal stripes. And once you do this, comparison between these two things, you will get a mask. And after applying the mask, you sort of get some basic harmonic percussive separation. So this is like 2010, which is way before deep learning. Cool. Yeah, so today we will basically going to talk about, deep learning based source separation. Um, yeah, they will require some convolutional neural network, and that's why we need to look into that before we started. But the core idea is that, well, there will be some fancy neural network that will get all the different spectrogram out. And our goal is to compare that with the ground truth. Of course, when we started, these will be really bad. But over time, hopefully we can measure the difference and improve that over time. And that's what we meant by, training the model. Cool. So this is the thing we will look into. But before that, we need to sort of understand what convolutional network is working on. Cool. Um, cool. Let me grab the slide. Now I'm not quite sure whether they are coming or not. Maybe they thought this is like too boring. Um, Let me find the CNN slide. Have you taken any machine learning course? The CNN. You are in? Okay. Where is it now?
What do you mean?
I mean, like where, like, yeah, transformer. Oh, that was quick, actually. Is that deep learning or just machine learning? Machine learning. And it's now doing transformer. I mean, when I took the machine learning, usually it started with like random forest and then SVN. And then I mean at the last several class, people talk about any deep learning stuff.
Done like rainforest. It was like
Just deep learning. Oh, okay. And then CNNs and then transformers. Then likely this is too easy. Anyway, we could just go over it. Just more like a recap, I guess. Um, CNNs. But basically, some of the source separation model are basically based on CNNs because technically what we are trying to do is something like UNet, where you have the input and output is actually the same shape, right? So input is like spectrogram, output is like spectrogram in another format, like a mask. So basically you are doing some UNet, and UNet is usually, CNN based. So that's why. Um, Anyway, we will talk a little bit about CNNs, likely too easy, but I guess some of the high level intuition, just to recap. Um, so anyway, CNN is just a way that we can learn reusable local pattern detectors. So this is widely used in computer vision, but also used in music and audio. So in deep learning class, usually you look into images, but as we talk about, music can be represented as piano rolls, where you have like pitch and time. But also for spectrogram, again, the same like time and frequency. So you can also apply CNNs to music and audio, although they have like slightly different meaning, asymmetric X and Y axes. But basically the core idea of convolutional neural network still holds, where that's like translational invariant, but also those reusable local pattern detector. Um, so, CNN sometimes, go too deep into the details. You somehow forgot what's the main goal of CNNs, but, the CNN, the core idea of convolutional neural network is that we are looking for reusable pattern detectors. So the filters that you are trying to learn with those CNNs the main intuition is that these could be reusable to nearby pixels. So, if you can learn, a filter, like a detector for the penguin, you should be able to just apply it to other penguins in the same image. But also you should be applied to something in penguins in another images. But at the same time, there are like different scales of detectors. Sometimes, if you look into the beaks are important to identify whether it's a bird or not, so that you can classify it into penguin. But at the same time, you want it to be reusable. But at the same time, these beak detector hopefully can also extend to generalize to other, patterns that you can find in other images. So this is basically the idea of CNNs, where you have like large scale, patterns and small scale patterns, and you want to learn this pattern and apply it to different images, different part of the same image, or, in other images. So that's essentially what CNN is trying to do, looking at all the images or, all the music in piano rolls, what are some of the reusable patterns that you can find? And that could be big, that could be small, but that's sort of the idea. Um, so, this is likely you No, what is this? It's a convolutional neural network, a bunch of convolutional and pooling layers. And in the end, you will flatten it into like a super long vectorized representation. And then you will go through a bunch of things that we are familiar with, fully connected layers. But the core of convolutional neural network is this, 2D convolution. Again, likely you know what this is. But basically you are just doing, element-wise multiplication where you have the input and you try to map your kernel onto these and try to see what are the sum of these element-wise multiplication. So, if you take this kernel onto this input and you do this like element-wise multiplication, you will see that it's like a perfect match. Everything sum to one, everything times into one. So this is sort of like similar to when we are trying to do the Fourier transform thing, right? You have that different sign frequency, different potential frequency component, sine wave with different frequency, and you have your input signal, and you just do, element-wise multiplication. When there's a perfect match, then everything will be perfectly synchronized. So it will be a maximum value. When there is a mismatch, one is positive, one is negative, then it will cancel out. So that's basically the idea. If there's a perfect match, everything should be, positive times positive, negative times negative. So it should be maximum value. So in this case, it will be 9. That's the maximum you can get because, thinking about assuming everything is just 1 or negative 1. But once you slide through different part of the images, now this is another perfect match, then some of those would cancel out. So you get a negative 1. And the same here, some of those will cancel out. So negative 1. But for this, again, perfect match. So you get a maximum activation of 9. So again, similar to what we have in Fourier transform, where you are, analyzing by doing this multiplication or dot product or convolution, basically. So now you see that, high activation, basically, when you see a pattern that's close to your kernel, then you get a high activation. But for those that doesn't have a perfect match, then you get a low activation. So that's essentially how. But you can also try on different inputs and outputs. So in this case, there's no match at all. In this case, there's no match at all. So everything is like 1, 1, 1, and at the bottom is like 5. But in this case, if you have a different, detector, now you're detecting the other direction, the other diagonal pattern. So the kernel is the pattern. The input would be things that you want to detect. Then you see that the output will have a 9 at the, top left part where you see there's a perfect match, but everything else, there is no match. Um, so kind of similar to, SDFD, where you are just matching your kernel, but in Fourier transform, where your kernel are different sine waves. And now you are just applying these kernel onto the input. So anyway, the goal of these convolutional layers is to try to learn these learnable kernels. So these things are being learned from the data. So you look at a bunch of data, you see what kind of, kernels, these filters, these pattern detectors are more important than others. And so, potentially it could be detecting, the boundaries, detecting the colors, detecting different shapes, and you will get a bunch of different channels or activation maps. And then you use those to compose, something bigger, a more complex, features over the layers. So that's basically what convolutional layer is trying to learn. So each kernel detects a local pattern that can be reused in the whole image or in other images. And the goal is to learn these kernels. Um, anyway, so that's how they work. And there's also consideration of padding, but I think we could skip this. But basically, you want to pad it so that the output will be the same shape. So basically, you could do 0 padding. That's usually what people use so that your output will be the same as your input. Um, So that's pattern equals same. This is usually when people doing convolutional neural network, you use that to keep the output of the same size as the input. It's much easier to work with. You'll see it in the homework, in the programming assignment. We also do striding, which means that we could just jump rather than, slide through it one by one. We can do a jump, but that's kind of straightforward. If you do a jump, then you can sort of like downsample the images, and you can aggregate information more aggressively. So that's the idea. You could just jump. This case, jump for 3 pixels at a time, then you get a much aggressive compression of the inputs. Another thing is about max pooling, but basically max pooling, the idea, the core intuition is that now if we are doing mostly classification, then we just care about whether you detect that pattern. You don't really care precisely where that pattern is coming from, especially when, the resolution is very high. So, reducing some of the resolution, but you still keeping where you find that peak activation. So think about this as like a beak detector, like for penguin, like or bird detection. Then in this case, you just want to know at the top left, there's some beak over there. You don't really care exactly which pixel it occurs. So in this case, once you do this max pooling layer, you downsample it into only 2 by 2, from 4 to 4 to 2 by 2. You still know that at top left, there's a beak. Top right bottom, there's another beak, but you don't necessarily need to know exactly where. So you reduce the resolution, but you still keep the activation and detection outputs. Cool. So that's a very quick review of what convolutional neural network is. You just go deeper and deeper. So usually you started with like 3 channels or 1 channel, RGB and grayscale 1 channel. And over the time, your resolution will shrink, but at the same time, the channels will increase. So the channels are the different features you are trying to detect. And the resolution goes lower and lower, but at the same time, you have more stuff to detect because now things become more complex. And that's the intuition behind why resolution reduce. At the same time, channels increase because now you are learning more and more nuance about the objects or the features that you are trying to do. But now you care less about where exactly they are. You just want to know whether you detect something at that rough position. Question on this? Cool. Um, cool. I mean, I think these are just some animation to see what convolutional neural is doing. But basically, you just scan through it, just like a printer scanner, not printer, to see where they are. But basically, you likely notice that in the programming assignment. So this is like the first channel, and the second channel you will have another detector, but basically you scan through it again. Now you get, the other channels. Anyway, just the same animation. And then you apply the pooling layer where you just, for each single, 2 by 2, you potentially just grab the maximum value of that so that you can do downsampling. So this is still like a more realistic example than previously we saw because, 16 by 16, and nowadays people are usually doing, 1024 times 1024 image classification. So, it's much trickier. Cool. Um, so this is something we could do. A toy example is that you started with like 16 by 16 images, and the goal is to see whether it's a cat, like a binary classification. Then you can do this convolutional layer, 143, max pooling, then you will downsample it, like you basically downsample it half because you are using pattern equal same so that the shape will keep. And when you do max pooling, you will downsample the shape. So now you get the fourth channel of 8 by 8 images. And then you do it again. Now you get like 8 channels of 4 by 4 maps. and then you flatten it. Usually that's the last thing you do, and then potentially going through a lot, several more deep, linear layers, and then at the end you just output like whether it's a cat. So it could be just one single value, or if you are doing multi-class classification, then there will be multiple values. Um, but anyway, there will be a cat image, hopefully, or a dog image, or whatever image. Um, so you can also do, multi-class classification if you change the last layer into three. So, in PA, we will do multi-instrument classification. But anyway, 16 by 16 should look like this. So technically hard to judge whether it's a cat or not. Um, cool. You see this in our PA, where basically you would take this 64 by 64 spectrogram. It looks kind of blurry, but you can actually tell this is like a electronic organ kind of thing, because everything just stay with like full spectrum, and you don't really see a decay at the higher end. So basically, it's likely an electronic instrument, because most acoustic instrument, you cannot stay with like maximum output. And there's a clear cut after, 3 seconds, and everything just gone. So this is like more likely an electronic instrument. And, if it's a wind instrument, when you have, wind or string, when you put the full efforts on blow in the air, or, scratch through it, then you will keep the spectrogram. The energy. So you can sort of kind of tell by just looking at the spectrogram. This is likely not a piano, because piano, once you hit it, it will just soon decay the energy. So you can do something like this. Well, technically, I think these are the answers of the assignment. Anyway, yeah, but anyway, we would just do some, CNNs to see. I think we could skip it for now. Cool. Um, cool. I guess lastly, what are the benefits of CNNs? So first, it learned local patterns. And these patterns is invariant to shifts, which is technically called translational invariance. So that's the core of CNNs. So your patterns should be, can be moved to different parts of the image, and you should still be able to detect. So that's something we could use. In spectrograms, everything should be time independent, where, this sound could happen at, um, first second of the audio, but it could happen in the second part of the audio, and it should be the same. The piano should sound the same. And we just want to reuse the learned patterns across different parts of an image and across different images. And that's why we are doing CNNs. And the core reason why we're using CNN is because it has a higher parameter efficiencies against a fully connected neural network. I guess this is more fun. What does the CNN learn? Likely you've seen something like this, but basically these are some of the CNN kernels in a trend. AlexNet. AlexNet is one of the iconic early year CNN, convolutional neural networks. So this is like the first convolutional neural network, the first layer weight. So if you look at these weights, you can see that this is like a pattern, like an edge detector. So basically this will see, if there's white, black, white, basically this is like a line detector. You see that there's like a line with that width in this direction and that direction and this direction, this direction. So there's a bunch of line detector, and there's also like stripe detector. So these are stripe detectors in different direction. There's also color block detector. So this is basically detecting this pink color. This is detecting red color, green color. So there's like, just like single color detector. There are also contrast edge detector, where you see the different colors and you see the contrast. So anyway, it's detecting, and this is like a chessboard detector kind of. You see that these are black and this is white. So this is like sort of like detecting that cross sign kind of thing. And this is also another checkboard like detector. Um, yeah, so basically these are the kernel that these model learn. And you can look at also like in the second layer. Now, second layer is much harder to see because the second layer, convolutional layer, is actually on top of the first layer channel. So you don't really know what these things are doing. Have you seen these? Yeah. So anyway, this is sort of like a glance into what's going on with the CNN kernels. So this is another figure showing that, what these kernels actually being activated. So these are the images or part of the image that trigger these kernels. So you can see that this is basically like an edge detector. And this one is like a color contrast detector, but this is just a green block detector in this case. And this one is more like a checkboard detector. So, these things also have this like texture pattern like that. Oh, boundary detector, color detector, things like that. So once you go over on the more and more or deeper and deeper into the layers, you will see that these CNN kernels will become more complex. So in the second layer, now you see circle detector where you just or spiral detector. And this is like corner detector, which is pretty interesting because it's basically just a L shape in a random place. But it will sort of like help you to identify like the window or the doors. And deeper into the third layer, then now you see grid detector and you can even see human detector. This is like very early in like the third layer because human is a very important feature in ImageNet classification, where you see in human, usually you just immediately send it to certain classes. So the kernels it learns base also depends on what type of data set and classes you are trying to classify it into. Anyway, the deeper you go into the model, the more detailed patterns or nuanced texture you will capture. So this is like sort of like almost the final layer. Now you can even see there's like logo detector where it just look at all the different logos, and this is like um, you know, filter detector. So anyway, you can also look into the activations, which is interesting. Can you guess what this is? Yeah, there's no way. Yeah, it's actually a cat. Yeah, but this is sort of like what the model is looking at. So this is like sort of like the different edge could be different activation. So this is sort of like the right hand side of the edge. So because of the sunlight, it will have, this is the right side of edge, and this is like the left side of edge. So, the model has to, and there's actually a sort of like a things here. This is basically just a, lower contrast of the cat. But anyway, this is just a cat. You can sort of see this is basically like a rough shape of that. It's like a color block detection. And you can see the cat here kind of. So this is like more, not detecting the boundary, but more just detecting the raw value of the cat. Um, yeah, so brightness and contrast. If you increase it, actually you can just see the cat. Um, Cool. So these are some of the detectors you can see if I increase the brightness and contrast. You can see that these detectors are looking at different boundaries because, different boundaries, they have different, because of the light, you will see different sort of like edge. So some of these detectors are detecting the right side of the edge. This is more like the top side of the edge. this could be something else. But anyway, they are looking at different part of the images. Cool. This is also a very interesting paper where it just not a paper. It's like the iconic Stanford curse. They have this like experiment. They just do it for they did it for the course itself. But basically, they are just trying to see this image, and they apply a gray block on top of this image, and they try to just move this gray block around this image and try to see where it can do a good classification or not. So basically, if it's red, meaning that, we can put a gray block here and it won't affect the output label. But the gray block, if it's somewhere around the face of the dog, then the accuracy will drop. It will not, actually classify it correctly. And so it's interesting, because it's like basically looking at the dope face rather than, some other features. But in this case, it's like, well, this is a car, obviously, but what features help this model to look at, to believe that this is a car? So you can see that it's actually more likely on the wheel rather than, other parts of that. So this is like a interesting way to sort of like doing interruption or ablation to see which part make the biggest influence on the classification result. And in this case, if you block the dog, actually it will likely assume it's like people. The class will be people rather than an Afghan hound. Um, Anyway, so actually nowadays, if we are using visual transformers, now you can also look into the attention metrics to sort of like see what these are. So these are sort of like kind of like the attention metrics if you're doing visual transformer, where visual transformer is just like doing some CNNs or doing some patch-wise CNNs or patch-wise filter learning, and then you use transformer to do all the attention thing. Then this is likely what the attention map would look like. So you grab like different patches of the images and you want to aggregate that information and you will apply a self-attention, then that self-attention will likely look like something like this. It will attend more to, important part of the image that's helpful for the classification, but not the other part. So this is like a early exploration and, later some, ideas like this gradually evolve into the idea of self-attention. And that's why nowadays you see some of these things. Cool. Any question on this? Cool. So this is like a fun experiment to sort of like reverse engineering what the CNN is looking at. So you can see that CNN relies on these parts mostly to do this classification. Cool. So that will help us to do talk about the demox thing that we want to talk about. Okay, let's go back to the source separation part. Oops. Cool. So as I said, what we want to do is just to do this mixture, spectrogram, and some CNN-based neural network all the way into, different channel of spectrogram. And, you want to compare with the ground truth so that you measure the difference and then use that difference to train your model. So that's essentially how. Let's skip this for a minute. So this is like not state of the art 2019, but actually it has a newer version which is more recent, 2023. So sort of like state of the art, but not state of the art at the same time. But this is one of the most iconic representative open source separation model that you can just go GitHub and download it to use it. So basically, this model is CNN, mostly CNN based, and it's a model called UNet. But basically, what you will see on all these encoder is basically something like you know like a CNN basically. So you grab all the waveform as input. So in this case, oh, actually we have to talk about this. So we talk about the spectrogram thing. It's much easier to look at. But actually some of these models are actually doing just directly on the waveform rather than spectrogram. So it's pretty much the same. You have the mixture, you get these, waveform out, and, you want to compare with ground truth. And, on Monday, we basically talk about why this could be challenging. So you have to be clever about how you define the loss function, because, just taking the difference between these two might not be the most effective way to define the loss function, because of the phase, basically you invert the waveform is still the same. So you likely want to do something else, potentially doing FFT and then compute the difference on the spectrogram, because, FFT is technically, you know, back propagable. But on the other hand, there's also some other definition that you can, some other loss function you can do. But anyway, you want to use the difference to train the model. So this is like the box. So you can see that the inputs and outputs. So inputs will be like a waveform as inputs, and the output will be, for different waveforms. That would be the different channels or different sources that you are trying to do. So for example, I don't know, vocal, bass, drums, and others. I think that's what the box is doing. So vocal, bass, and drums, and everything else will be put into the other channel. This is like their assumption, but it works most of the case, because bass is much easier to define. Drum is also easy to define. Vocal is also to define. Others is a bit tricky to think about. Think about like synthesizers for violins. It could be keyboard. It could be, synthesizers. It could be, like an orchestra. So it's a little bit tricky to define. So in this case, the marks just treat them as everything is like other. But you can do, vocal, bass, and drums at least. Cool. So this is what they are doing. Basically, it's just a bunch of, convolutional layers. So you see convolutional 1D, you have like C in out, this is the channel, kernel size, stride. So K equal A, meaning that at each time it's like 1/8 kernel. So learning about something about that A value stuff. And then stride is 4. So it jump sort of like halfway through the kernel size. The kernel size will be 8, but each jump you jump 4. So this is sort of like doing SATFD, where you have the window size is 8, and then the stride is like 4, hop size is 4. So you have like 1/8 filter, but every time you jump, it's like 4 pixel away. So that's the first, convolutional layer. And then you do a ReLU, and then you go through another convolutional layer. Now the channel will increase again, but now this time it's more like you don't change the size, because it's like kernel equal 1, stride equal 1. So that basically just do linear mapping, but it will be 1D convolutional layer. So you can see by the size. So usually these lengths actually have some meaning. So you go from a larger shape stuff into a lower size things, and in this case, it doesn't change the shape. But anyway, once you go through that, you will go to the other encoder, go through a bunch of encoder. And lastly, once you go into the middle, it will become a much shorter things, because the things will be in very high resolution. I forgot what exactly sampling rate they are doing, but likely 16K hertz-ish. There will be a lot of input, but after several layers, hopefully you will become much smaller. In this case, they're using hidden size 2048, but this is like a LSTM. We will talk about it later, but anyway, it's just a recurrent neural network, but think about it more like another neural network to sort of get the contextualized information surrounding to summarize the whole signals. And once you do that, now in the decoder layers, you use the same CNN. So CNN can sort of like downsize something. It can also upsample something. So for the decoder layer, again, it's like convolutional layer. First, you do this convolutional layer, but at the same time, you use this transport convolutional layer. But transport convolutional layer is that basically you use convolutional layer and with the stride so that you can increase the size of the output. Um, anyway, it's just another convolution layer. When you compute the size, there's some way you can actually apply a larger filter on top of something and use a larger slice so that you can expand the size of the output than the input. But basically, this is generally called a UNet structure. So this is what the original UNet paper is about. So interesting, the original UNet paper is for biomedical image segmentation, and this is like a conference published on the conference for, sort of like, medical image segmentation. So you could do, cancer, tumor detection or things like that. But basically, UNet is about you have an image and your output will be the exactly same shape. And that's what segmentation is doing. Because, think about, I have some figures. So think about, tumor segmentation. You have this image of a brain, fMRI. Your output will be the same thing, just that now you want to mark these region with, potential, things that might be bad, or, you just want to mark different parts of the brain that you should look into. And also, depth estimation. This is also where UNets could be helpful, where you basically just look at the image and the output would be the same shape, just now in a different value. But also the image segmentation, where you look at an image and basically you're just coloring with different image parts. So these are where UNets will be most helpful, but also in our case, source separation, we are doing exactly the same shape. Um, cool. So this is basically UNet. So UNet is just something like this, where you have a bunch of things that just compress the inputs all the way towards something compressed, and then you want to expand it on the way up. And the more interesting part of UNet is that there's this skip connection thing in the middle. And UNet come from this idea of it's like U shape. But a total example of UNet is that, you can do 16 by 16, downsample it into 8 by 8 for channels, downsample it into 4 by 4, 8 channels in this case, 4 channel and then 8 channels. And then on the way back, when you want to do convolutional 2D, you can do convolutional 2D, and then you use a assembling layer to scale it back to 8 by 8 for channel. So this is when you can apply the UNet idea. So you can, again, convolutional 2D, and then you do this upsampling layer to expand it into 16 by 16. So the idea of UNet is basically, have this skip connection, because these two things are essentially the same shape. So you can grab these things and just copy them, put it here. When you are doing the last layer, you get information from the second last, but and also on the previous one. Question on this? So basically, UNet is just combining high level and low level features at the same time. So now you can have access to, the low layer features, but, also some low level features when you detect the first layer, because those will be very, edge-like features. But all the way when you coming back from the, very compressed representation, those will be high level information. So the blue one will be more high level. The orange one will be more low level, but you can combine them to do your final segmentation. Cool. So, basically combining low level and high level features, low level, high level features, low level, high level features, low level, high level features, all the way in the whole process. So UNet is very useful in all different case, but I guess also something worth mentioning is this, style transfer thing. So, style transfer is also, some of those are based on UNet. You could do, just turn an image into a specific style. You could also do colorization, historical image or even videos. Nowadays, you can do colorization of films. You can find some on YouTube. You can also do semantic synthesis, where the input is just segmentation of different part of the image. So this is like 20 second. You can see that it's doing very good. A more, impactful field is sim to real, where you basically grab like GTA scene and you can turn it into real-ish, realistic, um, footage. So this is kind of important, because a lot of time when we are developing like autonomous driving cars, people use these sim to real um, environments so that they can mimic what an autonomous car could happen. Because, in GTA, you can hit someone, you could potentially create some certain scenarios where your car, your autonomous driving system should be aware of. And that will be, lower cost than, hitting someone on the road. So, sim to real, it's a big topic because, they have a lot of implication in developing, robotic applications, but also autonomous driving, where you want to put like a robot into real life. Before that, you want to try it with a simulated scenario environment, but that environment shouldn't be too realistic. So you want to do this sim to real thing, and the goal is to create a realistic but simulation for your agents to learn from. Cool. Anyway, that's what the Demox is. So we also have these skip connections to connect those. So this is a more recent model. So this is, I would say, still state of the art, at least for source separation, open source one. So in homework two, you will play with the Moises one that's like commercialized and definitely state of the art. But this is one of the few open source models that has very good results. So what's going on in this version of the Demox is that it's actually doing two things at the same time. So you have the time domain module, but you also have the frequency domain module. So as I said, STFT is actually differentiable and you can back propagate back to that. So the right-hand side is essentially the same as what we see here. So we basically grab this and put it here, but now you can actually do a separate channel where you just do STFT first, you get the spectrogram, and you do all the same thing. But now it's like 2D convolution. So you do all the stuff all the way until you get the original, get some spectrogram back. And then you do ISTFT. Again, ISTFT is also differentiable. So you do ISTFT back, and then you add these two things together. So this way is like, well, we don't want just frequency domain only module because these module doesn't have the base information. So they tend to be not the best. But we also don't want it to be just, time domain module because time domain module is much harder to train. So in this case, it's like, well, let's just do it both. We will have these, two stream. But one thing interesting is that in the middle of this LSTM, now they replace it with a transformer encoder. But basically, transformer encoder is just a by LSTM where it's like contextualized and try to aggregate information around these two streams. Um, anyway, you get best of two worlds. So in PA3, we'll basically just explore these. So the second part, where's that? The second part of PA3 would be that. Cool. PAC. Cool. Yeah, the second part is basically just using demux. So demux, you can actually just install it with pip install, so shouldn't be any issue. Basically, this is what you need: pip install demux, and that's it. It will just install demux. If you're interested, you can actually look into their code base. Um, it's no longer maintained, but it's still a nice things to look at. Um, anyway, it's a huge code base, but basically, it has a very good command line interface. So what you can do is that on command line, you can just directly just do the mux, two stems, drums, test that wave. In this case, you will just get, drums and not drums. You can also do it in another way, demux that separate that man in Python. These is essentially the same way how you do the command line things. So, you can do this. Basically, you will just separate the input into drums and not drums. So you can listen to it. Let's bring the sound coming out. Nope, didn't. This will be the drums. Pretty good. No drums. You can still hear them. But this is very convenient because basically what you need to do is just pip install the box and then you can just use it right away in Python. You can also do several other things. It doesn't has to be just drum and not drums. You can also do the whole you play vocals. There's no vocals and others. Anyway, that's basically what this PA is doing. Not a lot of coding, basically just explore what the mux and HPSS is. Not essentially doing a lot of stuff, mostly just calling package. Cool. Questions on this? One thing interesting is that you can actually test it on GPU and CPU. So on Google Colab, you can actually set it into GPU mode or not GPU mode. So you should set it to GPU mode. Otherwise, you might need to wait a long time for these. But once you are done with GPU mode, one thing you could try is just to try it on CPU and see how slow it is. It's not the worst, but you definitely see the difference. It will go from less than 10 seconds to something take 1 to 2 minutes. So it will be at least 50 times longer usually. So to experience what deep learning require for CPU and GPU. Cool. Um, Cool. I guess that's the boring part. So there's also a lot more, more ongoing stuff. So separation, so separation extends beyond the common, things that people usually talk about with just pop music, especially, guitar, piano, bass, stuff like that. But there's also tons of different things. So in this case, choral music separation. This is more on the study, much harder to do it because you don't have a lot of data set. So this is choral separation. Oh, my heart this night rejoices as I hear. So this is what this model can do in 2022. So it's not so far away. It's like thing we did in 2022. So what we are trying to do here is that because we don't have a lot of like data set for choral music, so what we did is basically we bought a very expensive, I think it's like 200 or 300 bucks, like a choral synthesizer, and then we just synthesize a bunch of choral music and see if that helps to do choral separation. So you can take a listen. It's not the best, but not too bad. You can definitely hear a lot of like artifacts. This is alto. Do you hear the soprano here? The tenor.
Oh, my heart is like rejoices as I hear.
So sometimes you hear the bass and alto, and this is bass.
Oh, my heart is like rejoices as I hear.
So you can definitely, hear some of those. And this is how we got this data set, which is pretty cool because if you just use boring sound fonts like the one you get in MuseScore, this is what it sounds like. Just like ooh, doesn't make much sense if you want to increase your data set. So this is another one. So this is the So this is what we can get with just only vowels with the the expensive sound that we have, but it's just singing ow, 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 only, and it's not expressive. So we can also even do more data augmentation so that now this become more expressive. So there's like dynamics. But still, it's just vowels. So actually, this software you can also synthesizer. It's expensive for some reason because you can also do words. So that's essentially what the data augmentation look like. So we get a bunch of these, expressive with word synthesized results for some of the choral music, famous one, so that we can expand the data set. And recently we are also doing, it's like ongoing. So we are doing something for a cappella, which is pretty cool because again, now it's even worse. Like a cappella, we don't really have any data set at all. So choral, at least there's some data set, but for a cappella, we pretty much have nothing. So we are looking into some of the way, we could also do this, but this is not technically for a cappella. Like a cappella is more modern. But we are also looking into can we use like AI cloning algorithm to do it. So, now we have a lot of like speaker cloning, like deepfake, but can we do it for a cappella? So, singing voice cloning can be used in a very bad way for deepfakes. Someone tried to clone Drake's voice in their work and they upload to YouTube and they got sued. But what if we could, use these AI cloning model to sort of try to increase the size of these, a cappella music separation models training data? That could be some other way to potentially use them in the positive way. It's ongoing. Hopefully, we'll get some results, something like this. One thing about a cappella, which is interesting, is that we have like vocal percussion. Actually, I just gave a talk yesterday on that, so I can grab some demo for that. Should be fun. Then this. Let me see if I can find it. So one thing interesting about a cappella is that a cappella have beatboxing, the vocal percussion. So we actually just grabbed the mux, the thing that we just talked about. The mux is for pop music, so you will have drums, vocal and bass and everything else. But we basically just use that drum separation model onto a cappella and see if that work for, vocal percussion, beatboxing. And surprisingly, it's not doing bad, which is interesting for me because it kind of sort of suggests that, we are doing great on vocal percussion. So that it sounds actually like drums to these, source separation model. Kind of laggy. Hopefully we could get it. Let me pause this slideshow. Let me see if I can find it. Cool, found it. But it's not showing. Cool. Anyway, just a teaser of what we are trying to do. Where's my cursor? So this is like the inputs. This is like Hakka language. In Hakka language, it's like a language spoken in Taiwan and also southern China and also Southeast Asia. And this is what we can get by using the drum separation model onto this beatboxing part. Which is interesting. So once you actually fine tune this model using our data set, you can actually do better, but this is not bad at all. So now you can actually fine tune it onto beatboxing, and now you can see what's the difference between what a drum model would be like, and this is like the vocal percussion. So I think that the kick drum is much full now, and the thing is not actually captured nicely in this vocal percussion when you are using the drum separation model. It's usually just rather than the air sounds, because that's not in the original training data. When you do drums, it's metal-like sound rather than that airflow sounds. Which is interesting. So basically, we just grab that drum model, and you see that the performance is like 4.22. This is like the higher the better. But once you fine tune, you actually do 7.62. That's the SDR. So the way how we see whether your output is clean compared to the original one. Another interesting finding is that when you do it with, there's actually a pre-trained specific model, Demox. Demox has several versions. One of them is actually specifically trained for drum separation. And actually, when we grab that, it actually do worse. So there's sort of like an interesting finding is that when you don't really be specialized in drum separation, you actually do a pretty good you get pretty good results just to see, pretending, out of drums, bass, vocals and others, lots of those vocal percussion will be allocated into drum track. But once you specialize this pop music drum extraction model, then it becomes worse. But anyway, you can fine tune the model to adapt more onto, a cappella. This is another example. So this is one with Demox drum separation. So pretty much really bad. But once you fine tune it, you can actually extract pretty nice. So this is much harder because in this case, there's pitch sounds, which is much harder. Those are for tom-toms. Um, Anyway, we are interested in this because we want to build a cappella practice app. Hopefully, we will get it done at some point. But soul separation, this sort of like showcase why soul separation is important because you have to do soul separation. You get a mixture recording of your rehearsal. Then what's the point? You still cannot get each single track. If you want to see whether, if you are alto, you are singing in the choir, and you want to know whether you are doing good, then you should be able to extract your voice so that you can do some analysis rather than, well, now this is the mixture and there's nothing you can do. So that's sort of like showcase why source separation is sometimes or usually the first step of a lot of like MIR text later you want to do it. So you have to do some source separation to extract the track that you're interested in, and then you do analysis so that provide feedback back to the practice. Cool, just cool ongoing work worth sharing, hopefully. Something else. This is choral music separation, and I just talk about a cappella. This is a very interesting thing I want to just share, but this is not based on soul separation, but it's fun. Anyway, is that good? Funniest thing. And you have like tenor. You have a mezzo soprano. So this is actually AI generated, like the harmonization. So when I grab like mezzo soprano, the other two parts are generating on the fly. And now like, okay. So now you can, that's my laptop sound effects. Wait a second. You're gone. Anyway, it's fun. You could try it. But this is again not soul separation. It's more you know, music generation, music harmonization technically, which is cool. Anyway, there's also some other things we could talk about, query by audio, so separation. This is interesting because, now you are not just, predefined sources, but now it's like, can you provide an example so that to hint what source, what sounds you want? So in this case, you have a mixture like this. And potentially, you know, you could just record a short expert of that for the sounds that you want to. So, this is like a different things. So think about, on stage, you want to have a source separation model and you don't know exactly what the ensemble will be like. So you have a mixture source separation model, but now, before the performance started, you just ask them each of single player to record, like a 30-second or 1 minute solo. And then you use that as the query to do this source separation. So this is like a way to think beyond, just predefine target. In this case, you could just grab that query and get the outputs. Of course, the result is not as good as, predefined categories, but now it can extend beyond those, predefined instruments. You will see this in our case. We will talk about this next. But, in PA, not PA, in homework too, you will experience this. Cool. Full break soon. Enjoy or enjoy some of the midterms. Do you have midterms?
Yeah.
After? Okay, yeah. I don't know exactly what full break is for. It's like cheer after midterms or prepare for midterms. Yeah, it's always like, I don't know. Yeah, cool. Yeah.